Okay, it's 12:35. So I was mentioning to the people earlier that Mark Overvac has bowed out and will not be giving lectures next week. So when Chongyin is finished, I'll start on redox flow batteries. And then after that, we'll start on fuel cells. So Chongyin, it's all yours.
Okay, thank you, Jeff. So we will continue with this water insert electrolyte first, and talk about the halogen intercalculation cathode later. So last time we mentioned this water insert electrolyte is in terms of conductivity, it's acceptable compared to the organic systems. So, but what's more important thing is how we're gonna extend this stability window of the aqueous solution to like from 1.2 volt to the 3 volt. So this is a sum up for the most recent effort to do that. Actually, with 28 molar or even the big with other sorts, we actually extended the window more than 3 volt. So which means we can use like moly sulfide or titanium oxide or even LTO as an anode. And for the cathode, we have plenty of much more choices like LMO, which is pretty stable in the aqueous system. And we also show using the high voltage lithium cobalt oxide. And also Yamada also shows using a 5 volt nickel manganese oxide, but it didn't work very well. We will talk about why later. So right now we need to explain why we be able to extend this stability window so much. So it has to related to the thermodynamic change of the water, right? So you cannot counting on adding some additives to form a better passivation to achieve that. That's at least a 1.5 volt extension. So for the further part is going to be the thermodynamic change. I thought I think I need to change back. Yeah, okay. So the first part is thermodynamic of the water. So I'm gonna borrow this picture again. So we all know that we can easily change the pH value of the aqueous solution to achieve this kind of widely shifting of the stability window. But why? It's mainly because the hydrogen evolution, the reactant of the hydrogen evolution in water actually is a proton. And the peroxide groups, hydroxide groups is more easily being oxidized in the water than the water molecule itself. So when we changing the pH value of the aqueous solution, we actually largely changing the concentration of the proton and hydroxide groups. So according to Nernst equation, if you're changing the concentration of the reactants, you will largely changing the reaction potentials, right? And another more important thing is that's the first part. We're gonna talk this first. So in water in salt electrolyte, it's kind of very unique because you actually limited all the water molecular into the lithium ion solution shell, which means we will so we will both damage the largely damage the concentration of the proton and the hydroxide groups in this aqueous solution. So which means the reactant concentration will be largely reduced. Another wild thing is if you can turn all of the water, like limit all the water molecule into the first solution shell, the activity coefficient of the water will also be largely reduced. So as a result, the whole water activity will be like totally reduced. So there is scientific evidence, solid evidence showing that. So we all know that if you put in a lithium metal into the water, it will be a disaster. You will have a violent reaction to create hydrogen and heat, right? That's why lithium metal is so so dangerous. But if you put the same lithium metal in the water in salt, you can barely see any reaction going on. So that's the very direct evidence showing that the water activity being diminished. Oh, sorry. Another evidence is that when you measure the vapor pressure of the this is diluted lithium tetrahydride water solution, and this is 28 molar water in salt. So you are after you calculate the water activity based on that, you will see that the dilute system is almost one, is as same as the pure water, right? But in the water in salt electrolyte has been like 10 times lower than the pure water for the active water activity. And the next thing is the thermodynamic of change of the lithium ions. So the same next equation, if you increasing the lithium ion concentration, you will certainly lift up the equivalent potential of the lithium chemistry in the electrolyte, right? But another thing is the activity coefficient also affect a lot, because if you limit to the coefficient to the 1, even you left the lithium ion concentration to 28 molar, you only have like 50 millivolt increase of the reactive potential. But in real case here, in the water in salt electrolyte, the 28 molar has been achieved like almost 250 millivolt increase of the lithium iron phosphate equivalent potential, which means compared to the concentration, the activity coefficient of the lithium ion will be even significantly increased, right? So we think that's mostly due to the dramatic change of the lithium ion solution solvation structure. So that's a very complicated stuff. So we don't talk about the details today. But the benefit of this is actually you left every lithium ion chemistry up at least 0.2 volt. So like the anode, like moly sulfide, which wasn't inside of the stability window of the aqueous electrolyte. Actually, right now we can push it up, and in this science paper, the moly sulfide is pretty stable inside of the water in salt electrolyte. But the downside is some kind of high voltage cathode is also being left up, so you cannot use the cathode with the reactive potential very close to the upper limit. But we only talk about the thermodynamics of this whole electrolyte, which is not so unique for this system, because for the lithium tetrahydride salt, because we can achieve the same effects by the other high solubility salts like lithium nitride or something. Right? It can also achieve like 21 molar and achieve the same extension. But more unique for the lithium tetrahydride salt, the high concentration lithium tetrahydride salt, is that according to the normal electrolyte structure mode of for the electrolyte we normally use, it's like if you have a 1 molar lithium salt, it will be like fully deassociated with the lithium ions, right? So the lithium ions will be fully solvated, and you will have a bunch of free anions. That's the normal model of that. But in the water in salt electrolyte, you actually making the water to lithium ion ratio to like 3 or even 2. So which means in average, you don't have enough water molecular to solvate even for the first solvation shell for all the lithium ion. So the whole nature chose another way to reduce the overall, another way to form another different bulk electrolyte bulk structure in terms of reducing the overall free energy. So actually in this water in salt electrolyte, forming the 2 domains. the domain 1 is actually barely have no water in that. Most of them is close contact ion pairs of anions, TFSI anions, and the lithium ions. And in the domain 2, you have like fully solvated lithium, not fully solvated. At least you have 4 more fully solvated the first shell of the lithium ions, and a much less anions inside of domain 2. This structure actually being proved by neutron scattering and modeling. So in this way, you will have a domain 2 as forming a fast transport channel of the lithium ions, right? And in domain 1, you have most of the anions in that, so it's forming a large vehicles, making the whole diffusivity of the anions much slower. So in this way, that's why in this kind of high viscosity electrolyte, you can still achieve a very good lithium ion transport. And the anion diffusivity is so low that's another reason why we achieve a very good lithium ion transference number in this electrolyte. But
Hi,
how?
Chun.
Yeah.
Hi, Chun. Just I have a quick question about this domain 1 and domain 2. Since they have a different type of structures, why would the domain 1 and domain 2 they don't choose to phase separate into completely different phase, but they still sort of mix with each other, but at the same time keep as 2 domains instead of mixed as 1?
Yeah, actually, it's this kind of liquid structure is you cannot consider that, compare it to the solid materials. So it's actually exchanging very fast. So which means it's not a stable, very stable structures. So it will have an exchange maybe between the lithium ions or even the whole domain in like form factors. So, and the whole like 2 domains in the scale, it's like a sub-nano scale. So in the large scale, it still looks like a homogeneous system. But we have done a lot of measurement in the Argonne National Lab with this kind of water insert electrolyte. Every time we use X-ray to do the diffraction, we can still see this kind of instead of the diffraction rings, we still can see the spots for the diffraction signals, which means you still can get some kind of order in this kind of structure. So in some level, you can claim that it is actually some kind of nanoscaled phase separation in this kind of electrolyte. So does it make any sense?
Okay, thank you.
Okay.
Yeah, thanks.
So yeah.
I also had a question along the same lines, because the domains themselves are not charge neutral then, right? If you draw them like that.
Yes.
But I guess you already answered by saying that they are nanodomains and they change like all the time. So
yeah, it works like larger cluster of the cations and a large cluster of the anions. Right? So in the large scale, it's still neutral, but in the very small scale, it's just like normal salt.
Okay.
Yeah. But the thing is, this structure actually is still a bulk structure. But to us, the more important structure for the battery actually is a structure very near to the electrolyte surface, right? Which means actually in the specifically in the double layer of the near the electrode surface. So on the surface in the double layer, it will be totally different from the bulk structure, because for the cathode, it normally has a relatively positive charge inside of electrode, which means it will attract more negative charged stuff, which here is more domain 1 type stuff near the electrode surface, which means you will it will has a much lower water concentration on the surface during the reaction, right? Electrochemical reaction. that's why we always has this kind of asymmetrical extension for the electrostability window.
Sorry, I couldn't quite hear you.
We normally has it's much easier to getting the promote the window on the cathode side, but it's always very hard to extend the window for the anode side. Only because on the anode side, for the relatively negative charge, it will extract more lithium ion with solvated water on the surface, which will elevate the water concentration on the anode surface. So so in this way, we actually, that makes sense that we need other thing, like phenomena to try to extend the anode side. Otherwise, it will, the lithium tephoside, even with a highly concentration lithium tephoside, it will acting as other salts like lithium nitride to getting like 2.2 volt, like 2.2 or 2.5 volt versus lithium like limit for the anode side, right? So that leads to the next very unique thing here is with the lithium highly concentrated lithium tephoside salt, we actually found it can form a very good passivation. We can still call it SEI on the anode surface. So that's a very solid, we have a very solid evidence, all kinds of evidence showing that we're forming SEI layer on the surface, which half of them is lithium fluoride, and the another half is mostly lithium oxide or lithium hydroxide. We cannot actually tell the difference by XPS, right? And slightly lithium carbonate. So that makes people actually very confused, because you only have the lithium tephoside salt in this electrolyte. So why the lithium tephoside salt can be decomposite at 2 volt? It's a very unusual thing, right? People actually don't believe that at the beginning. So Dr. Stoll actually published this paper on JAX a few years ago, trying to explain why. So in his theory, all the oxygen and carbon dioxide coming from the gas who was dissolved into the electrolyte, and the lithium fluoride is coming from the decomposition of this L2 lithium 2 tephoside complex, which is ion pair we talk about in the domain 1, right? But I don't think it's the real case here, because first of all, the oxygen solubility and the carbon dioxide solubility is being largely reduced in this kind of water in salt compared to the normal aqueous solution. And another thing is the tephoside salt it's very hard to believe that the tephoside anion can be decomposite, like, not to mention 2.9, even 2 volt, it's very hard to believe that. So after that, we actually dig that more. And another French group also, actually in the meantime, they also published a paper claiming the same theory, same as us. So the real case here is, at least at the beginning, the initial cycles, you're still getting some water be decomposite, right, on the anode surface, and the hydrogen evolution will left some hydroxide group behind. But the unique thing for this electrolyte is you cannot dissolve any lithium hydroxide in this aqueous solution anymore, because you already have the saturated lithium ion in this solution. So it will be deposit on the anode surface, the lithium hydroxide, and with the hydroxide group will attack the lithium tephoside anions, make it to release more fluoride, and forming the lithium fluoride and deposit on the surface again. So in this way, you can getting a very good dense SEI passivation layer on the anode surface. So that's why we're getting a very good window extension on the anode side. Okay, so the last part is a fairly minor fact, but I think it's also very important because in the view of like water like hydrogen evolution reaction, the different material we choose for the electrode actually acting as a different catalyst for the water decomposition, right? So, but we cannot actually choose the active material surface, and we cannot choose a different carbon. So we have to use them. But at least we can choose the right can collector surface to reduce the water decomposition. So we actually found that for the anode side in this water system, aluminum gonna be the best current collector because we won't go below to the 1 volt. So it should be okay for us to use aluminum as current collector. For the cathode side, the best choice should be the titanium, but it's so expensive. So probably the stainless steel is still working good enough for the cathode side. So with this, all this effort, we can achieve a very good stability window for the aqueous system for the lithium-ion battery. And I just want to show some best performance lately we achieved in Maryland. And the first system is, I have to mention that right now, pursuing a larger stability window is not only thing we want to pursue now. Because if we want to push this aqueous electrolyte to the market, we have to reduce the cost of the whole battery, whole electrolyte, which means we need to reduce the salt usage, right? So, and in the meantime, we need to still achieve the same or even better stability window. So in this work, we use a 4.5 molar lithium synthesizer, which is largely reduced salt usage. And we add a little bit KOH to promote the SCI formation. And most importantly, we're adding the urons to forming forming like acting like the water stabler, and also like trying to reduce the salt usage. In this way, the aqueous battery with LMO and LTO, which is 3-volt batteries, we can achieve a very good cycling performance in a full pouch cell. And another work here is we use UV cured polymers, hydrophilic polymers, to act in like the water stabler, and also trying to reduce the salt usage. And that's a very cool, unique technology. So it only takes like 5 seconds to cure the whole polymer, and it looks like pretty much like a solid. And like cool thing is it won't lose any water if you expose to the air, so you won't have other this kind of problem in the other aqueous-based gel electrolyte case. So with this electrolyte, we can actually getting a similar very good cycling performance, and even can build the flexible aqueous battery working in the open air. So that's pretty much everything I want to say for the water insulated electrolyte. So is there any questions I can? Okay, I think.
Chongyin, so the sodium, so you use the potassium like as a additive, but do you worry about this potassium also intercalates into your LTO anode? Because it's also ions. It's also cation.
We didn't see this kind of potassium has causing any problem, because I think mostly because this KOH is not dissolved in the water here, because as I said, you cannot dissolve any alkali anymore in this kind of water insulated electrolyte. So I think most of this KOH being dissolved as into the urine with the urine. So which means the hydroxide group actually under the potassium anion actually didn't dissociate. so it won't participate in the chemical electrochemical reaction here. So we didn't see any. We actually measure test the material very carefully and didn't see any sign of this intercalculation.
Okay, thank you.
I have a couple of questions about the UV cured polymer on this slide.
Okay.
So that looks really interesting. Is there, so before when we talked about the nano domains in the pictures there, does that kind of thing apply here, or are those domains different now because we have these polymer crosslinks that are more locked into place and maybe there's less fluctuations? And then my other question was, do you need additional liquid here for the electrolyte to be able to go into the pores of the electrodes?
Yes, thank you for your question. So actually, we cannot call it a polymer electrolyte because it's not looks like solid, but actually it's still a hydrogel electrolyte, which means the polymer is still polymer and the liquid electrolyte is still inside. So I think it didn't really change the structure of the liquid side. So the only thing here is just this kind of polymer acting like a filter for this and the backbones of the whole polymer system. But the real working electrolyte here is still the same as this kind of liquid one. So I don't see any difference here. And you don't need to add in any more liquid. So this thing looks like solid, but it still maintain a very good ionic conductivity.
I see. Cool. That's very interesting. Thank you.
Thank you.
Yeah, this is really cool. The UV cured material. What electrode materials are you using for the right side here of the plot?
Yeah, sorry about that.
Because
we still
is pretty good.
Yeah, we still stick with LMO and LTO, and in terms of capacity, I need to note like every people working on that side is still worried about mostly worried about the anode, right? So every like capacity we're showing here is actually the anode capacity. It's not like the full cell capacity. So the whole capacity and the energy density is still low.
So it's normalized to the grams of
it's
anode.
normalized. Mm-hmm.
Okay.
I was just curious that with this 4.5 molar or 12 molar LiTFSI, is the cost comparable to lithium-ion, modern lithium-ion batteries?
No, it's still way more expensive than the organic system. Because in the organic electrolyte system, the electrolyte cost is compared to the electrode material, it's very low. So, but lithium TFS source here it's still very expensive. So even with like 4.5 molar, it's still very high cost. So unless we can find another way to extend the stability window with a much lower salt concentration, or even using a much cheaper salt, I don't think it will open up any kind of big market for this kind of aqueous batteries. So actually, Jeff have some conclusion, but yeah, I think this overall in terms of academic way, it looks very cool. But I don't think in this stage it have any kind of market for this kind of aqueous battery, because the whole cost is much higher, and the energy density still cannot compare to the organic system. So and Jeff actually raised a very good question here. Is we didn't actually test the high temperature performance a lot. So I highly recommend the people back in Maryland to do the high temperature holding and high temperature storage for that, to see how it works.
I just have a comment on the last point, like Jeff put here, about testing this at elevated temperatures, because still related to the nano domains you mentioned before.
Yeah.
I'm just wondering, have people? I mean, as you mentioned, it's not exactly two different phases, so there shouldn't be called phase diagram. I don't know if people have done this nano domains mapping of these nano domains as a function of temperature. I think one concern is that if you increase the temperature, will these nano domains like disappear? So it's very useful if someone could just for the fundamental science purposes to sort of to map these nano domains, just like a phase diagram for the bulk materials. Just one comment.
That's a very good comment. Actually, I think we should, if we want to study that more, we should invest more like energy and time on that. But the thing is, it's very hard to measure these small structures because it won't show any signal by the X-ray diffraction or scattering. The only thing so sensitive to water or lithium is actually using neutron. So the only way we can like slightly measure the scale of these kind of domains by neutron scattering. So I think you are right. We should actually change the sample temperature and use a neutron scattering to see this kind of signal, this kind of ordering is that the scale is changing or not. So it will give us a sense that if this kind of or even this peak is still there, so it will give us a sense that this kind of ordering will be diminished during the high temperature or not. So. Okay, I guess there's no further questions, so I can go to the next part. The next part, I want to talk about this halogen convention intercalculation chemistry I reported 2 years ago. So in this work, actually, it's still based on the aqueous electrolyte. And right now we want to transfer that to the organic system. So that requires more efforts on that. But today I'm only talk about the aqueous part. So why we call it halogen convention intercalculation chemistry? It's a very odd term, right? So we actually use a halogen convention reaction to deliver a high energy density. But we also use the graphite intercalculation chemistry to provide a very good reversibility of that. So this story starting from a few years ago when I trying to use this sulfur chemistry in this water in salt electrolyte. So it turns out it's a very interesting finding that the sulfur chemistry in this high concentration electrolyte acting more like a solid-solid reaction instead of like liquid solid reaction in the normal DME based electrolyte. So the reason is actually we found out even this kind of lithium polysulfide being dissolved in the water, it's forming a very good phase separate with water in salt electrolyte, which means you don't have any anion exchange between that. So in this way, if you put sulfur chemistry in the water in salt electrolyte, the whole polysulfide part will be like limited to the cathode layers. So it's more like solid-solid reaction. So as a result, you can get a very good cyclability of the sulfur chemistry in the water in salt electrolyte. But actually, this work makes us think more about like, can we find another system is pretty similar as a polysulfide or sulfur here? Actually, we can. So we find out the halogens in here is a lithium like salt, lithium bromide, lithium chloride salt. If you have forming any kind of concentration of this kind of salt with aqueous solution, it's forming an even better phase separate with water in salt electrolyte. And even though this lithium bromide, lithium chloride salt is highly hydrophilic, right? So, and has a huge solubility in the water. So that makes us think, because in theory, lithium bromide, lithium chloride salt actually is a very good choice as active material for the lithium-ion chemistry. It has a huge theoretical capacities, and the redox potential is high because it's higher than 4 volt, but it's not so high, so our electrolyte can handle that kind of potential. With this finding, the phase separation with our electrolyte, we actually have a chance to design this brand new cathode chemistry. And another very important piece of information coming from my colleague, who was very expert of the graphite intercalculation compound. He actually told me that the halogens is very easy to intercalculate into the graphite and forming a very stable intercalculation compound. And I think that's, in combination, I think that will give us a very good chance to design a brand new cathode with a high energy density, right? And I was so surprised that nobody have ever think about using this kind of bromine intercalculation in graphite before as a to design a cathode chemistry before. So we try that and try to design the whole system and using the water electrolyte, and it turns out working very well. So the thing is, so the whole process is we design this ratio between the lithium bromide, lithium chloride salt with the graphites, and mix them and make them as a cathode material. So when it contact with the water in salt electrolyte, the lithium bromide, lithium chloride salt gonna absorb a little bit of water from the water in salt electrolyte, trace of water, forming this kind of very a small hydrate shell to elevate the whole reaction. Right? So during the charging, the bromide will be oxidized first into the bromine, and it will intercalculate, because the whole reaction will happen on the surface of graphite, because that's the only thing has a good electrical conductivity here, right? So the whole redox reaction will happen on the surface. So as soon as the reaction happens, the bromine will be intercalculated into the graphite. So the whole ratio between the lithium bromide and the graphite was being well designed. So when you use up all the lithium bromide salt, all the bromine being intercalculated, forming the stage 2 graphite intercalculation compound. So with all the bromine being consumed, the voltage goes up and began to oxidize the chloride. So the chloride, the same story here, the chloride being oxidized to chlorine and continually intercalculate into the graphite. So in the end, after we consume all the lithium bromide, lithium chloride salt, the whole graphite is become stage 1 graphite intercalculation compound. Okay, so the whole, and it's totally reversible during the discharge. So in this way, we actually use the advantage of an intercalculation reaction to provide a very good reversibility and protect the highly reactive like bromine and chlorine, right? But we actually get rid of this kind of dead weight or dead volume of the oxygen layers, oxide layers, and use a much better intercalculation host as graphite. To me, it's a perfect host for the intercalculation reaction. And we also use the convention type reaction of the bromine and chlorine, right? So we actually getting a very good energy density of that. So combined, we actually think this chemistry have a very good potentials. So people will actually think this this chemistry as compared it to the dual ion batteries. Actually, it happens a lot during the reviewing of all papers. So for the dual ion battery, what happened is for the anode, it has a lithium ion intercalculate into the graphite, and you have anions intercalculate into the graphite, right, in the cathode. Here, you also see these kind of anions being intercalculated into the graphite in the cathode. So people will think, oh, maybe it's the same as hybrid batteries as dual ion batteries, but it's not, because in this kind of battery, all these kind of anion the cation is from the being already dissolved in electrolyte. So this kind of hybrid battery depend on this amount of the electrolyte, right? But here if you see it from the cell level, the only thing during the charge, the only thing comes out from the solid cathode layer is lithium ion, right? It will comes out from the cathode and being inserted into the anode. And during the discharge, it will going backwards. So it's still a rock shell batteries, right? And the whole reversibility is amazingly good. And we check the discharged electrode. As you can see, besides this kind of graphite particles, you can still see this kind of lithium bromide, lithium chloride salt is well distributed outside of the graphite. So that makes it still a very good solid cathode chemistry, as every solid we are currently working on.
Can I ask a question here?
Yeah.
Okay, so, when I look at this, I just say this is incredible. And what I want to know is, how many cells did you have to make before you got this thing to work? Was this the first cell just worked, or was it 10 cells or 100 cells? And, while you were doing this, were you working 24 hours continuously every day because this was so exciting? Tell us a story about this, how the success took place.
Yeah. This idea actually happens, I think it's 2018, when Ji Cheng, another first author, come to our lab. So we are very good friends. So we talk a lot about this kind of new ideas. So at that time, I want to try a new chemistry for the ecosystem, because we actually run out of any good options for the aqueous battery to improve the energy density, right? So I think because a lot of people are working on the zinc bromide batteries, so I think using halogen actually not a very bad idea. And so I talked this idea with and I have this kind of discussion funding with this kind of phase separation at that time. So I want to try that, and I talked with my colleague, and he told me we can actually intercalculate this stuff into the graphite. He is a graphite expert. So so the very next day we designed this chemistry and just mixed them and made a I think it's 5 batteries, and 5 of them all works very well. We are so excited to see these beautiful profiles, 2-stage profiles, right? So because we already designed this, so we intentionally put same molar amount of the bromide and chloride in that, because we know the bromide chloride 1-to-1 will be very stable in the graphite instead of using all the chloride, right? So as soon as we see this kind of beautiful 2-stage profile, which means it works very well as we design. So and to your question, actually the first batch of battery already showing the very positive results. So but the thing is, at the beginning we don't know how to handle this how to handle the graphite, how to pick the right graphite, how to mix them, how to make them to a good dry electrode, and we're still using the liquid water in salt. So the overall Coulombic efficiency is not so good. It's only like 60 or between 60 and 70 and 80%. That makes us very frustrated. So I actually spent almost I think 8 or 9 months working on how to optimize this ecosystem to get a very good Coulombic efficiency, and spend the last 1 year to prove the whole reaction is the same as we designed. So including the how does it really intercalculate into graphite? That's the first question. And what's the staging structure evolution, and what's the most important, what's the implant structure? Because we actually find out this intercalation compound is a highly dense, highly impact intercalation compound in all of these kind of graphite intercalation compounds, even higher than the lithium, because lithium is forming the carbon-6 lithium 1, right? But here you can, in stage 1, you can forming the carbon-7 and 2 halogen atoms, which means the carbon should be like 3.5, right? So that makes that everything, especially this one, makes us achieve a very high energy like a capacity for this kind of chemistry. So I spend most of the time like.
Let me ask another question. You know, so you found the voltage curve right at the beginning.
Yeah.
First cells, right? First
yes.
cells. And then you were working on figuring out the mechanism and the Coulombic efficiency improvement and all this. When did you guys decide to push the trigger to write a paper? Like, I think if I was doing this, I would have pushed for a paper without so much backup, you know, just with
I know.
say, here's the voltage curve and a couple simple experiments. But it sounds like you guys waited for almost a year to collect all the backup data that you wanted.
Yeah, at least I think at least 1.5 years to write a paper and submit it. So to me, I think that's a trade-off, right? So if you want to publish paper on like Nature, you need every bit of evidence to support you. Otherwise, if you only have the battery performance data, you don't even get a chance to send out for reviewing. So that's actually, I don't like this system right now, because it actually delayed our publishing for our very significant funding. But the thing is, I think this funding is so huge that I just don't want to waste this opportunity. So I'm pretty sure nobody else will doing the same thing at that time. And I actually spent, because all this chemistry is so unique. You need to use a water insert electrolyte, right? So I don't think there's huge amount of groups working on that already. And you have to think about how to use a bromide chloride salt as an active material. And you also need an expert like my friend on the graphite to know how to put the graphite inside and make it intercalculation reaction, right? So I think I thought I should take this chance and wait, be patient, and get a full proof, like full evidence to support everything, and then just write a paper. So actually, in the end, the writing papers part is actually the most easy thing, because you get the whole story already like boiled down, right? So yeah. That's
a wonderful story. So I'm sorry to send you down the garden path with a long story, but I think it's useful for people to hear this stuff. You know, I gotta tell you, like, this is it's if this actually works in the cell level, you know, and is working in lithium-ion batteries, this is like Nobel Prize type of thing. It's just so off the wall. I'm serious. This is so off the wall.
I still think we need to make it work well.
Well, I mean, it's so off the wall, so new, so different. It's really quite incredible. So I really appreciate that story. Thank you very much.
Thank you. Okay, so so let's continue with that. So so as a result, we getting this kind of battery performance as a voltage profile. It gives us like overall 240 capacity, very close to the theoretical capacity as we designed. And the average voltage of this cathode is around 4.2 to 4.3 in the aqueous system. So the overall energy density in theory is higher than any even high nickel materials we are working on. And the only thing higher than this, in theory, higher than this work is sulfur chemistry, or of course the oxygen, lithium oxygen, but we lithium L. But we won't talk about that. That thing has a huge amount of issues. But lithium sulfur is higher than that. But if you see the volumetric energy density, it's almost comparable with like high nickel materials in theory, and even higher than sulfur, because higher sulfur, it has a huge amount of carbon in that, so it damages the volumetric energy density. So in the end, we actually can build a full cell with this cathode with the graphite anode. So how we gonna run this graphite anode in the aqueous system, that's another story. I actually published a 4-volt aqueous battery paper on that. But it's more like a trick we played. So we well protected this graphite anode. So so we can deliver this kind of 4-volt like full cells. And on paper, it delivers much higher energy density compared to any kind of non-aqueous system in the material level. But we still, this only a very early age, like very early prototype. It's more like a proof of concept. So for this chemistry, the advantage is first, like we have a very high energy density, right? So even compared to the state-of-art materials, it's comparable. And this Hell stays 250 cycles actually is followed by because of our later effort trying to transfer to the organic system. Actually, we can achieve a much stable cycling and longer than 250 cycles at I think it's 1/5 C/O5 rate. And most importantly, we actually missed this on our paper. We didn't actually say that on our paper, but I think Jeff and Tessa will be more excited about is it's low cost, because you don't have any transition metal in that cathode anymore. The only thing we need is just a bromide salt and chloride salt, which is very abundant in our sea or myodine, right? And more importantly, for this cathode, you don't need any kind of high temperature process anymore. So only thing we did in this paper is just mix the normal lithium salt, like bromide salt, chloride salt with graphite particle, adding some PTFE as a binder, and make it by the dry electrode method. And that's it, no heating. And you might need to bake it a little bit, but get rid of the last trace of water. But later, we actually found out you don't need even do that to do that. We can even use the lithium bromide, lithium chloride salt with a little bit of structured water, and it even makes the whole kinetics of the battery even better. So that's a takeaway. So I don't think we have time left. So yeah, so
that's a good place to stop for today.
Okay. Okay.
Yeah, so Chongyun will finish off his section on Monday. I'm not sure how long it will take, but however long it takes, that's fine.
I think it only takes like 10 minutes more, I think.
Okay, well, it'll take about 10 more minutes, and then I'll start on redox flow. I'll send everybody the notes for redox flow over the weekend, and I've almost got homework 7 ready for you folks, so you'll enjoy homework 7 as well, I'm sure. So any questions about what Chongyun was talking about just there at the end?
I have a question on the staging of this bromide on graphite. Let's say if we apply the lattice gas model, introduced earlier by Jeff in the course, can can we say that in this case, because the bromine chloride atom is so large than lithium, are there more like stream-mediated attractive interactions? That's because
yeah,
when you look at the chart, yeah, go ahead.
Yeah, that's more. I think we need to discuss this detail next time, because that's a very complicated model. It's very different to lithium or other alkaline cations. So we actually spent a huge amount of time explaining this kind of staging, because apparently a lot of people, chemistry people, measure that. I think a few decades ago, but nobody actually calculated that and say, oh, why it's acting like so different with the lithium here, right? That's Jeff's another work, very early work. So I think we need to discuss. Maybe after I showing this part, maybe we can discuss more details on that. But I can assure you this system is very interesting compared to other like alkaline and ion intercalculation.
Okay, thank you.
Thank you.
So quick question about the system. So the electrolyte is still the LiTFSI water insult for this, yeah?
Yes. Yeah. Oh, yes. In this system, we're still using the 28 molar, which is a mixed salt with lithium TFSI and lithium OTF. It's not purely about the window anymore, because for the cathode side, it's only like it's lower than 4.5. So 21 molar, 28 molar both works well. For the anode side, because we actually protect the graphite, so there are also not very different between this kind of 21 molar and 28 molar. But the unique thing we did here is we actually use the hydrogel we present earlier. The thing is, the reason is even though we have a good phase separation here, right? But you cannot guarantee it's not mixing, but you cannot guarantee you won't lose any kind of lithium bromide, lithium chloride aqueous solution being diffused into the electrolyte as a second phase, right? So that's why we need to abandon the liquid electrolyte and using the more like semi-solid electrolyte layer to prevent this kind of physical mixture. Does it make any sense?
Oh yeah, it does. I was more wondering actually about the cost aspect. Have you factored in that at the moment as well? I mean, aside if you don't have precision metals, but then your electrolyte is
yeah, actually at the beginning we didn't actually consider any kind of cost based on that, because it's like brand new scientific finding, so we didn't consider that.
Yeah, right now I'm not saying anything about the scientific finding or something. I'm just wondering about the cost. If you have to use this electrolyte, how's that gonna affect?
Yeah, I don't think we will use that anymore, even use the aqueous solution anymore. We need to find a way to transport this cathode into the normal organic system. In order to, one thing is to couple with a normal anode we are using, like graphite. Another thing is the organic system will always give us more stability than the aqueous system. So, and also, of course, the cost. The whole water insert system is too expensive. So, yeah.
Okay, thanks.
Thank you.
Okay, so I think that's a good place to stop for today. It's getting late.
Okay.
People probably have lots of experiments they want to do.